Hey everyone, in this video we're going to go over section 2.1, the tangent and velocity problems. We've got two main objectives for this section, the first of which we want to explore how limits naturally arise when attempting to find the tangent of a curve, and the other we want to explore how limits naturally arise when we are trying to solve velocity problems or find the velocity of an object. So first off, let's get a intuitive idea of what tangent means. So let's take a curve. This will be our x, this will be our y, and we'll be continuous everywhere. So tangent comes from Latin. Tangus, tangis, Tanges. It's Latin. But in Latin, or translated to English, it means touching. So a tangent line, and quite often we'll be talking about tangent lines, is a line that touches the graph. But where? So imagine we had a line. We'll say that. This line is going to touch the curve in exactly one point. A good way to visualize what a tangent line is imagine taking your pen, and if you could trace out the curve with your pen. How we always have this straight line, and it's trying to trace along the curve here. This straight line would be tangent to the curve. There's a property of a tangent line that we will explore and discuss later, and that is this tangent line points in the same direction as this curve at this point. Another way of saying that is the slope of the curve at this point is the same as the slope of this tangent line. And we'll go into more detail about that, but the big takeaway here is that tangent lines touch a curve. They effectively trace the curve with a straight object that continues to touch the curve in exactly one point. Later on in this class, we will explore techniques for finding the slope of this tangent line, but for now what we're going to do is we are going to approximate it. So, let's say we have, the same curve. And let's say we wanted to find the slope of the tangent line at this point. We'll call that point A. And we want to know, what is the slope of that line? The line that touches the curve at exactly one point. What we're going to do is we're going to use a bunch of secant lines. In a secant line, an easy example. On a circle, a secant line is a line that intersects the circle in two locations. So, what we want to do is we're going to use a series of secant lines. So, the first thing we're going to do is we're going to pick some point. We're going to pick a point close to A. So, right here. And we'll get the y value associated with that x value. And now we'll calculate the slope of the line connecting these 2 points. Then we'll move a little bit closer. Then we'll calculate the slope of the line between these 2 points. And we'll do that for a couple points as we get really close to A. We also have to do the same thing on the other side. So we'd pick a point that's close to A, but not right next to it, and we would get the y value, and we would calculate the slope of the line between those 2 points. And we would finally walk it back, and what we're trying to do is we're trying to see a pattern emerge in the values of the slope of the secant line. So let's start out with an actual example. So, we want to find the equation of the tangent line to the parabola y is equal to x squared at the point 1, 1. This is notation that the book really likes to use. They would say p 1, 1. In this example, you'll also see things like Q24. And what the book is saying is they're calling this point Q, and they're saying that it has coordinates 2, 4. And they're also saying that this point, we're going to call it P, and it has coordinates 1, 1. That's the way the book often writes it. I would personally write P is equal to 1, 1, or Q is equal to 2, 4. But that's just a matter of preference. As you guys are going through your book, if you see that, it means that. And if you see me write that, it means that. So, we've got this parabola. And let's draw it out. We're going to graph this thing on Desmos here in a second. And we'll get some actual detail in our graph. And then the point 1, 1 is about right there. So that is our point P. And what we want to do is, if we could take a pen, and if we could trace this curve, leaving the pen fixed at exactly one point, kind of like it's balancing along a curve, we could leave the pen fixed on the curve and tell that point, what is the slope of this line? What's the slope of the line that touches the parabola at the point 1, 1? Well, we need 2 bits of information for a line. 1, we need a slope, and 2, we need a point. So the slope formula, you guys might remember, the slope is going to be equal to y2 minus y1 over x2 minus x1. Same formula for slope that we've always used. Except for now, we want to find the difference. P has this coordinate 1, 1, and we want to find the distance to this curve. So the slope, or the formula that we're going to use, our slope is going to be after, now our y-coordinate is going to be given by x squared minus 1, the difference in our y-coordinates, divided by the difference in our x-coordinates, x minus 1. Same thing, we got the difference in our y-coordinates, and the difference in our x-coordinates is just down here. We've got a rule. We know what one of our y-coordinates is, because we want to find the slope between this point and some other point whose coordinates are x and x squared. So, this will be how we go through and find our slope. Now this is how, what's a good way of saying this? This is supposed to be an introductory, this is supposed to get your feet wet, introduce you guys to this idea. We're going to go through a series of guesses, and it's going to feel kind of at random. This is supposed to get you guys to observe a pattern, and then later on in this chapter we will develop a better algebraic way of actually solving these problems. But for now, it's going to boil down to picking a bunch of points. So let's work out a couple of these by hand. So what we want to do is we're going to pick some point that's further away, not further, how far, within 1. So let's say this is the point we care about. What happens when we pick x is equal to 2? Well, we know on this curve, when x is equal to 2, y has to be equal to 4. And now, if we want to calculate the slope between this point and this point, we'll call this point Q. Well, the slope between P and Q, m is going to be equal to 4 minus 1 over 2 minus 1. Well, that's going to be 3 over 1, which is equal to 3. So the slope between these two lines, or those 2 points, is 3. Solid. Now let's pick another point, and I'll call this 1. Now let's pick a point that's closer. let's say, well, what about when x is equal to 1.5? Well, our slope is going to be 1.5 squared minus 1 all over 1.5 minus 1. That's going to be 2.25 minus 1 all over 0.5, which works out to 2.5. So now the slope of the secant line connecting these 2 points is 1.5. I'm sorry, 2.5, not 1.5. 2.5. So notice how as we slide these points together, we're fixed at this point, and we checked the slope between these 2 points, it was 3. Then we checked the slope between these 2 points, and it was 2.5. Now we want to keep on creeping in. We've done 1.5. The next one we're going to check is 1.1. M is equal to 1.1 squared minus 1 all over 1.1 minus 1. Oh, that's going to be 1.21 minus 1 all over 0.1, which is equal to 0.21 over 0.1, which is 2.1. So notice how as we get closer and closer to this point, the value or the slope of the secant line is decreasing. It went from 3, went to 2.5, went to 2.1. So we're getting closer and closer. In fact, if we continue, let's say we go through the point, 1.01, our slope is going to be equal to 2.01. And if we go through the point 1.001, our slope is going to be equal to 2.001. So notice how as our values of x, and I'm going to say it again, as our values of x get closer and closer to 1, at 1, and also notice how we can't calculate the slope at 1. If we try and calculate the slope at 1, we're going to get a 0 in our denominator. We can never have a 0 in our denominator. You know, we can't divide by 0. So we can't actually calculate the slope at the point 1, 1. What we're doing is we're making observations about these values. Well, when we were at 1, we don't know. Nothing we can do. But when we were at 1.001, our slope was 2.001. When we were at 1.01, our slope was 2.01. When we were at 1.1, our slope was 2.1. And then when we were at 1.5, our slope was 2.5, and we plugged in 2 and we got 3. For what we're doing, 2 is incredibly far away from 1. Calculus is a lot like a chemistry class in that we're going to be taking a close look at values, taking a close look at numbers, seeing the way things relate, seeing the way things don't relate. A gap of 1 is fairly large for what we're doing. 1/2, 0.1, 0.01, 0.001, that's more in the ballpark of what we're after. I'm going to put an X there because we can't actually continue, or we can't calculate the slope at that point. But now we have to go the other way. If we go all the way back to 0, well, the y height is going to be 0. So at 0, our slope actually works out to be 1. And when we're at 0.5, our slope works out to be 1.5. When we're at 0.9, and I'm calculating these values the same way I did over here, I just have them typed out next to me so you guys don't have to watch me do arithmetic. 0.89, I'm sorry, 1.9, 1.9, and then 0.99, we had a slope of 1.99, and then finally 0.999, we had a slope of 1.999. Sorry that it got kind of messy, but take a look at what we have here. Once again, all these top values were calculated with this formula down here. What we're trying to do is, and these are all of our slopes, we're looking for the pattern. We're looking for the bit of information we can't solve for. And we're looking at this pattern to get information on what it appears to be. So if we increase from 1, 1.5, 1.9, 1.99, 1.999, can't get that value. And then on the right side of it, 2.001, 2.01, 2.1, 2.53. Well, if x could be 1, it seems like, I'm sorry, if we could plug 1 into this formula, probably shouldn't have put a x right there. If we could plug 1 into this formula, well, based off of this pattern, it seems like the slope would be equal to 2. And in fact, it would. Like I said, when we get to chapter 3, we will know without a doubt that the slope is 2. For now, this is the process we're going to go through. So we were tasked to find the equation of the tangent line. Okay, this part is where calculus ends. We have rationalized using calculus tools to get this slope. Now we have to find the equation of a line. Well, y minus y1 is equal to m times x minus x1. Point slope form, they gave us a point. Y minus 1 is equal to, and we came up with the slope, 2x minus 1. Oh, we can distribute, gather like terms. Y minus 1 is equal to 2x minus 2. Add 1 to both sides to get y is equal to 2x minus 1. Which is the equation of the line that's tangent to this curve at that point. Now I'm going to jump over to Desmos and I'm going to show you an animation of what this problem is actually getting at. Okay everyone, so this is Desmos. It's just an online graphing website, www.desmos.com. So this is our parabola. This red parabola is, well, y. I called it f of x is equal to x squared. And this is the point that we care about. We want to find the line that is tangent to this curve that touches this curve at this point. So going over what we did. So when x was equal to 2, let's open this up. So the first thing that we did, and I want to hide that one, is so we picked a point. We picked this point 2, 4. And we want to calculate the slope of the line connecting these 2 points. Well, we calculated that slope to be 3. You can see it down here, m is equal to 3. And this is a picture of that line. So, well, we don't necessarily care about the slope of the line between these 2 points. We want to walk this value of x closer and closer back to 1. So after 2, we guessed 1.5. Well, when x is 1.5, this y value is 2.25, and the slope that connects these 2 points is 2.5. We brought it closer, 1.1. Now our slope is 2.5. Bring it closer again, 2.01. Bring it closer again. Now it's getting hard to read, 2.001. We have to go from both directions to get this value. That's a subtle point, and we haven't developed enough mathematics yet for me to completely explain why. But we have to go from the other side too. So at 0, well, we found the slope of the line that connected these points. Then we brought it closer to 1 from the other direction, 1.5. Brought it closer again, 1.9. Brought it closer again, 1.99, and brought it closer and closer again. That one's mad at me. So the slope should be saying 1.999. Desmos likes to round when values get really close to each other. That's why there's a question mark right there. It's calculating the value. It's just not spitting it out. So, what's going on here? Let's let's take a look. So calculus is dynamic. Let's let this thing run. And let's slow it down a bit. So what this is doing is, this is a dynamic version of what I just showed you. We're taking this point, this black moving point, and we are sliding it closer and closer and closer to this point 1, 1. And as it gets closer and further away on the other end, this value is constantly being updated. That black value, that m is equal to 2.23, that is the slope of this black line. And now watch what happens as that black dot gets really close to that blue dot. Let's slow this thing down even more. It's getting closer and closer and closer to 2. And now we're going away. Now we're moving on the back side of it. So we're getting further away. Let me speed this up again, because that's not the exciting part. It's going to go all the way to 0 and then come back. Okay, as we get closer and closer, our slope is getting closer and closer to 2. So this is the trend that we're after. This is why we're calculating by hand. We're trying to figure out a trend in these numbers. And what happens when a is equal to 1? Well, our slope is going to be undefined. Because remember, to find the slope of this line, we're doing y2 minus y1 over x2 minus x1. You can't, with that formula, you don't have enough to actually calculate the slope of this point. So that's what we're doing by hand. We're going through. Let me switch back to the other video. So that's what we're doing here. And you guys, for the record, you guys are free to use calculators in this class. Typically, I don't let my students use calculators. There's no way for me to police what you do at your home, and I have no interest in trying to do so. So feel free to use calculators. Excel is a powerful tool. You'll see me use Desmos a lot. I'm gonna constantly recommend you guys get used to Desmos. If you guys are engineers, if you're going through Calc 3 differential equations, Desmos is a very powerful tool that can be used in a lot of different ways. But that's what we're doing. We are picking points. We care about this point 1, 1, and we are picking x values. These are all x values in a narrow window around 1. What's a narrow window? I wouldn't go more than a half of a unit in either direction myself. And we're using this formula. Y minus y1, or this one, for this specific problem, it's x squared minus 1 over x minus 1. We'll do another example and it's different. It all boils down to this same problem. y2 minus y1 is equal to x2 minus x1, and we're calculating the slope between the points as those points get closer and closer and closer. Let's do another example. So this problem is going to be a little bit different. I'll warn you off the bat, this problem is going to boil down to an estimate at the very end. We are not going to do many problems that boil down to a good estimate. We're going to attempt to be much more precise in our approach to our calculus problems. But let's go through this. The flash unit on a camera operates by storing charges on a capacitor and releasing it suddenly. The data in the table describes the charge in the capacitor after some amount of time. Use the data to draw the graph. We already did that on Desmos. And estimate the slope of the tangent line at the point where t is equal to 0.04. So that means we care about the slope on this curve, and we'll plot it out in a second. And we care about the slope at the point 0.04, 67.03. And so, once again, we're gonna estimate. We're gonna try and figure it out. The difference in this problem is that we're not given a function. In the previous example, we had a function. We had the ability to kind of discover, we could figure out any y value that was associated with a certain x value. Because we had that rule. Y was equal to x squared. in this problem, we don't have that luxury. We don't have a function. So let's take a look at what this data looks like when we plot it. So this is what the data looks like when we plot it. I've got all the x values over here and their y values, and they are represented by these dots. I've got a couple labels turned on that I shouldn't right now. And this x value right here, this is that point 0.04 that we're trying to figure out the slope of the tangent line at. So we don't have a lot of options. Really, we only have 5 others? 1, 2, 3, 4, 5. We only have 5 other points we can compare with this point. If we calculate the slope between that point and this point, or if we find that line, well, here it is. If we then move in, once again, we can't find the y value associated with any of these. Our next x value is at 0.02. And this slope, let's see if it'll let me move it. It will if I make it large and move it to the right. The slope of the line that connects this point, 0.02 and 81.87. Oh no, I have lost. It was, what did it say? Minus 700. Got it written down over here. Minus 742. Okay. We can't calculate the slope at that point, but if we continue this trend, and that's the label that I want, just after the point we care about, now we're going between the point 0.06 and the point 0.04. And that line has a slope of negative 607.5. So, without being able to get closer and closer, all we have to do is effectively make an educated guess. That's a good way of saying it. We'll make an educated guess about what the slope of the line will be at this point right here. I really hope this screen capture is getting my mouse too. Well, we know that's our point. Oh, where'd my label go? Uh, 607. I've lost it. So, we knew that at the point, let's say at the point 0.02, 81.87, we know that there was a slope of negative 742. Make it look like the other one. M is equal to negative 742. We're getting that value. Way to calculate a slope, y2 minus y1 over x2 minus x1. This is all the information we have, though. We know that the slope between this point and this point is negative 742, and we know that the slope between this point and this point is negative 607.5. We also know that these two x values are the same distance apart from the x value we care about. The book would say a natural solution. What mathematicians would choose to do is we're just going to take the average of those two values. We're going to figure out what the average of 742, negative 742, and negative 607.5 is. Well, that value, that works out to be negative 674.75. We can put that down here. We'll say, we will say the slope of the tangent is equal to negative 674.75. Oops. So, sorry, I'm trying to mess around with that too much. So, what we did is we're just going to take the average of those two values. The average of negative 742 and negative 607.5 is at negative 674.75. I don't like the sort of estimate approach. I don't like inferring, if you will. We're going to do very little of this inferencing. We're going to, for the most part, take a very methodical approach to finding exact values. Like I said, in this first section, they're just trying to get you guys to develop more of an intuitive idea of what tangents mean. So for now, this is the tool. These are the tools we have at our disposal. We would take the average of this tangent, or the slope of this tangent line, and the slope of that tangent line, and that's the best we can do in this situation. So the final example for this section, once I find where I put it. Okay. So an object, so think about it. If you're here and you move over to that location, the rate at which you change your position is equal to your velocity. We'll say that. Rate that you change, the rate that you change your position is your velocity. And so our velocity would be equal to our change in position divided by our change in time. We're going to use a triangle and call it a delta a lot. We're going to say change in position you could view as delta POS divided by delta time. These two mean the same thing. We'll use that notation a little bit more later on. So the rate at which you change your position is your velocity. Galileo, I believe it was, him and his friends, they observed that the rate at which an object fell was proportional to the square of the time it was in the air. That's a fancy way of saying that after a bunch of experimentation, Galileo figured out that the position, denoted by S, of a falling object after a certain amount of time is equal to 4.9 t squared. Its position, you could also think of its displacement, how far the object fell. How far the object fell after t seconds. So like I said, how far an object fell after t seconds. And what we want to do is we want to calculate the instantaneous velocity. The instantaneous velocity of a falling object after 5 seconds. So that's the thing. The big word here is instantaneous. When we're dealing with instantaneous, or when you see the word instantaneous, that's this limiting process. That's where we can't actually figure out the velocity at 5 seconds, but we can view the, or we can, what's a good way of saying that? We can't actually calculate the velocity at 5 because the velocity of a falling object is going to be given by s of t minus 4.9 times 5 squared all over t minus 5. The difference in our position minus the difference in our time. And that's why we can't just plug in t equals 5 into this equation, because we would get a 0 in our denominator. So to figure out the instantaneous velocity, what we want to do is we're going to do the same process. Let's get some values. Let's say s of 6 is equal to 176.4, s of 5.1. And once again, all these values are worked out in our book. I'm just copying them off a table. Copying them off that table. I can show them to you as I write them out. Okay. So our average velocity, like I said, change in position over time elapsed. Got this value, 122.5. And then, so what we're doing, this is a parabola. And how far the object fell as time goes forward kind of looks like this. This is our time, and this is our displacement as a function of time. Over here, when time is equal to 5, we want to figure out how much its position is changing. And so we're going to do the same thing. We'll calculate over here at 6. We go from the point 5, 122.5, up here to the point 6, 176.4, and would calculate the slope between those two lines. M is equal to 176.4 minus 122.5 all over 6 minus 5, which would give us 5.39. Like I said, for what we're doing, a gap of 1 is huge. A gap of 1, I personally think that the book only chooses to do a gap of 1 to kind of illustrate a point. If we continue, I want that one still. So if we continue, well, what if we move this point closer? Let's get a lot closer. Let's jump from 6 over to 5.1. Well, at 5.1, the slope of that line is going to be 127.449 minus 122.5 all over 5.1 minus 5. That'll give us 49.49. And so this is how I'm getting these numbers in the right-hand column. And as you look, as our value of x gets closer and closer and closer to 5, the average velocity, or the value of the slope, is getting closer and closer and closer and closer to 49. There's a point when you just call it. We could plug in 5.0001, but we've done enough so far to see that a pattern is emerging. When do you stop? When you notice a pattern. 49, 49, 49, 49 gets closer and closer and closer to 49. So we say 49. I would encourage you, so a lot of times books will not consider what happens at a previous event in time because time only goes forwards. That's more of a physics thing than a mathematics thing. For finding an instantaneous rate of change, you would want to also consider 4.999, 4.9, 4.5, and 4 as well, and you want to walk at it from two different directions. Physical limitations, time only goes forward, it doesn't go back. That's why they're only considering these positive values. For this problem, it's fine. Like I said, we're not going to be doing too terribly many of these. Your homework has, I think, 4 of them on there, 5 of them. For your homework, and I'm not done talking yet, 1 through 9, 9 odd. Okay. Go through and practice these. It's going to be a lot of getting values, and then watching this trend in the value of a slope. Let's see. Okay, briefly go over that. Okay, I do want to show you, so what we're doing largely, our slope is f of a plus h minus f of a all over a plus h minus a. Some of you might have seen that part before, but what we're doing is we're calculating the point. We care about this point f of we care about this point a f of a, and we want to increase it by a little bit. H is small. Students ask what is small. H, for what we're doing, we're looking closer at mathematics, physically closer at mathematics than we have ever done before. H is so small that it's hard to tell it apart from 0. And we care about the slope as we slide h closer to 0. More on that later. This formula with a limit tacked out in front of it is going to be primarily the focus of chapter 3. There's one or two things I want to introduce some notation to you. I forgot to mention this while we were doing it, so I want to backtrack. In that first example, where were we? Over here. And then, did it continue anywhere else? That's all we need. So, in this one, what we saw is that the slope tended towards 2. So what we want to write is the first bit of calculus notation we're going to use is this idea, and I'll give it its own page, of a limit. And that's what we're doing. I'm going to talk about this example in particular, but we've done it in all of these examples. What we did is we calculated the limit. And we're going to write just LIM, the limit as x approached 1 of x squared minus 1 over x minus 1. So what we did was we plugged in different values for x and then different values for x squared. And then we took a look at this pattern. 3, 2.5, 2.1. If I find the other page of my notes. 3, 2.5, 2.1, 2.01, 2.001. And on the other side, 1, 1.5, 1.9, 1.99, 1.999. As we kept on using that formula, this x squared minus 1 over x minus 1, and as we let x get closer to 1, this whole limit approached 2. The limit as x approached 1 of x squared minus 1 over x minus 1 is equal to 2. That is saying that the y values, or the values that we got from evaluating this fraction, as we let x get closer and closer to 1, well, they tended towards 2. And they tended towards 2. We can never get 2 because we can't plug x is equal to 1 into this fraction. But the observation we made about the slope said that those values tended towards 2. So this is our new bit of notation. What this is saying is we observed this trend in x values. Or we let the x values tend towards that value in this equation. The y values from that equation tended towards that value. Similarly for our other example, and I did this one all on Desmos, but the previous one, we'll go over to 3. I'm not going to do example 2 because once again in example 2 we didn't have a function. But in example 3 we did. We knew that the limit, as we let t get close to 5, and technically we would say from the right, but I'm gonna leave that up for now. The limit as we let t get closer to 5 of this 4.9 t squared minus, and I gotta find where I hid that value from me. Oh, it is now lost. Huh. Sorry, give me a second, guys. Okay, there we go. $122.5. Sorry, I lost it. All over t minus 5. So on this problem, the one with the position, we were using this equation to find our velocity. And as we let t get closer and closer to 5, the value of this fraction tended towards 49. So we have limits equaling numbers. This is going to be the idea that we're going to go after. This notation saying that, well, we've got this limit. The value is changing. That's the dynamic thing of calculus. We allow values to change. Oh, this lecture is getting kind of long at this point, so I'm going to wrap it up there. This is what you should expect. You should expect some sort of video like this in all of its glory every Monday, Wednesday, and Friday for this semester. I'll be jumping back and forth between handwritten stuff and stuff on my laptop. If you guys have any questions for me, you can email me, emfoley@alaska.edu. It's the one that's on Blackboard. If you find my personal email, please don't use my personal email. You can email me. You can even text me. I've got my cell phone number under my contact information on Blackboard. If you emailed me and I haven't responded in a timely manner, go ahead and shoot me a text message. That'll get my attention. And office hours, if you guys ever wanna, I can discuss this stuff with you. If there's anything I can do to help you, let me know. I want to be there for you. I want to help you guys through this. Calculus can be kind of difficult. It's different ways of thinking. But yeah, with that, I think I will set you free. Like I said, go off and do, I think it was 1 through 9. I have it written on Blackboard. Go off and do 1 through 9 odd for this section, and I'll post another video on Wednesday. Thank you.